We talked the other day about, DC and AC. So DC is what? What's it mean to be DC? Don't say direct current. I get that, right? What's it mean to be DC? As a function of time, everything is constant, right? Or at least very close to constant. AC is what? Alternating current, right? So what does AC mean? It means my stuff basically varies. We've got some interesting sort of finger pictures going on today. So so there's some fluctuation that happens, right? And typically, so here I've got actually two different types of AC waveforms on top of each other there on the right side. On the left, I've got what a very often what a DC signal looks like, which is, to be honest with you, not all that constant, right? It's pretty flat, but it's definitely got some variation to it. So usually signals have some DC plus some AC, right? And we said one of the important things is if I have something like this thing over here, this yellow waveform, this what I call square wave, that square wave can be thought of as the sum of sine waves, okay? And if I know how to treat a sine wave and I have another waveform that's a sum of sine waves, I can use the sine wave approach to handle the sum of sine waves. All right, and that makes analysis a heck of a lot easier. Makes it analysis easier because it means we don't have to do differential equations. And one thing you guys don't want to be here anyway, probably, but you really wouldn't want to be here if we had to do differential equations for the next however many years, right, or for the rest of your life. Differential equations are kind of, you bring them out for special occasions, all right, and we don't really, other than once we introduce them and learn dynamic systems, we don't deal with them all that much. All right, we deal with methods of steady state analysis. And the nice thing about those methods of steady state analysis is they're just like what you learned in 2111. Which even if you didn't like that, right, it's a heck of a lot easier than doing differential equations all the time. Okay. So this is our basic, we talked about a couple of different ideas, radio waves, we have modulations and stuff like that. All of your radio signals are sinusoidal, right? All of your phones in this room are transmitting sinusoidal signals. So it's just a useful approach for us to understand. And we deal with them all the time in ECE problems. So audio, power, radio, all that stuff, sinusoidal at some level, so they're important. So we spend a lot of time on them. So the other day, I talked about the sine function. All right, so when I say the sine function, so sine of theta is the way it's defined. Okay, so theta is by definition an angle, right? And by definition, I said, what are the units of that angle? Radians, all right? And I generally speaking don't refer to angles in radians. We use degrees more frequently because it's much more common. Now, and the drawing I have here is the sine function over 0 to 2 theta, or to 0 to 2 pi. Okay. Now, what do we know about the magnitude of sine of theta? What are the boundaries on sine of theta? What's its min and max values? 1 and -1. So we know this guy's got to be between -1 and 1. And so I put this x sub m multiplier on it. What was the name I gave to x sub m? Amplitude, right? Now, this is not what I would call a wave, though. A wave would be something that's a function of time. Like what I just showed you right there showed you how my voice was changing as a function of time. As time advanced, what you saw changed, right? So in reality, what we typically do is we say, okay, well, these waveforms have an angle that is changing over time. So usually this angle theta becomes a function of time. And I say theta is equal to omega t, all right, where omega is a angular frequency. It is the frequency at which the angle is changing. All right, and it has units of radians per second. There is never going to be an angle given to you in degrees per second. I've never seen that in my life. Okay. All right, radians per second is what we always have, right? So that just gets to the way, again, sine is defined. Okay. All right, so the way the relationship is usually kind of lined up is I say up here, I have x of theta is x sub m sine of theta. That's what I've drawn on the top graph. What I've drawn on the one beneath it is x sub m sine of omega t, where I've made this relationship that theta equals omega t. So basically these waveforms show me the same thing over 360 degrees, how this waveform is changing. The bottom one is showing me like if I had a voltage and I measured it in the lab, what it would look like, right, as time advanced. So what I can see for this particular waveform, when theta is equal to 0, t is equal to 0. So here's theta equal to 0. Here's t equal to 0. If I want to figure out the relationship between time and theta, I look at this theta equals omega t thing. All right, so if I went to, first of all, what angle am I at if I'm at a quarter of a period? All right, so I used the term the other day, a period, right? So a period is how long it takes for me to repeat. So if I'm looking at the picture on the top, how long does it take sine of theta to repeat? 2 pi radians or 360 degrees. Every 360 degrees, the value of the function is the same again. All right. So, all right. So if I get 1/4 of the way through a cycle, so, and that's the other term we'll use for a period, as cycle. Basically, how long does it take to get through one period? That's one cycle. If I get 1/4 of the way through a period, what's the angle at 1/4 of the way through a period? 90 or pi over 2. So if I'll write it as pi over 2 here in radians. So what time is that? What time do I reach that point? So it's t over 2, or sorry, t over 4, right? So the other day I defined this term t, the period, right? Let me skip ahead for a second back to my definitions, right? So I said period is the time that it takes for me to go from the beginning to the end, the amount of time it takes for the values to repeat, right? So the definition of a period, and Yahoo maybe has talked about this a little bit in 2254, we say x, whenever x of t is equal to x of t plus capital T. In other words, how much time does it take for the function to repeat itself? That's what that equation says. How long does it take? Capital T is the amount of time it takes for the value of the function to repeat itself. All right, so from one peak to the next peak, right? Or from one valley to the next valley. How long does that take? Okay. Or from one positive zero crossing to the next positive zero crossing. All right, that's, we use those definitions. Now, what I said here, so the capital T that I've written out here is when I've gone through an angle of 2 pi, I've gone through one full period, okay? And so one thing I look at here, we have a couple of relationships that are probably important for us, right? So I talked about this the other day, is I have the period is t. We relate the period to the frequency f, all right? So period has units of seconds because it's how much time it takes for this thing to repeat. So the frequency is how fast it repeats. So 1 over the period is the frequency. So what should be the units of frequency? 1 over seconds, which we said has, which, what do we call that? Hertz, right? Not a hertz, right? It's a name, all right? So it's 1 hertz, all right? So we relate all of that to the angular frequency, how fast this, basically how fast this angle is changing here. What we say that omega equals 2 pi f, or 2 pi over t, like that. All right, that's the relationship between all these two things. So if I look at this here, and I think in that context, right? So so 1/4 of the way through a period, so t over 4 is 1/4 of a way through a period, that's equal to pi over 2. I can do a quick check on that because I can say omega is always 2 pi over t, right? So if I say plug in t equal to 1/4 of a period, if that was t over 4, I get the t's cancel, and I'm left with, what am I left with? Pi over 2, right? 90 degrees. All right, and I can keep going with that. So if I go to half the period, t over 2, that would be pi radians, right? And then the whole thing just kind of repeats like that. So there's this relationship between angle and time, and it's important to kind of remember that, because oftentimes if I go in the lab, I don't always look to see the time delays and all of that. I don't often look at the values on this axis, but I often talk in terms of how much of a shift is there maybe between two waveforms in terms of how many degrees of a shift is there, all right? How much have they shifted from each other? I don't necessarily care about the timing specifics, but I care about how much relative. So the nice thing about this is I'll kind of talk about is the notion of using angles lets me talk on a relative basis between waveforms. All right. Whereas I don't care about the absolute time shifts. I care about the relative shifts. And we'll see where that applies as we go through more of this. Okay. All right. So the other day I said, and we're going to talk about this in general, we get all of our waveforms, whether I give you a sine function or a cosine function, we get everything in terms of cosine. And we talk about how much of a shift there is relative to cosine omega t. All right, so I wanted to define a couple of things here. So I said that for this waveform, there's basically three key parameters that we talk about. We talk about its amplitude, which is how big it is. We talk about its frequency, so how fast it varies, and we talk about its offset, right? When I say it's offset, what I mean is how much is it offset from being cosine at t equal to 0, right? So looking at this waveform here, is this, let's try to identify, this is very similar to what we did the other day, right? So I have this guy, x of t equals xm cosine omega t plus phi. So I want you guys to help me. First of all, I just want to remind, this is a function of time. So t is just a variable, stays t, right? But x of m, omega, and phi are all constant numbers defined for this thing. All right, so what are those constant numbers? What is, for the picture I've drawn here, what is x sub m? 10. X sub m should be 10, right? And I can see if I, the maximum value for cosine is always 1, right? So the maximum value of this function is 10. So x sub m must be equal to 10, all right? How do I determine omega from looking at this picture? How can I determine what the angular frequency is? Well, yeah, 2 pi f will tell me that. So how can I figure out what f is?
How long it takes to repeat.
How long it takes to repeat, which tells me not f, but tells me t, the period, right? So in this case, the simplest thing for me, if I go into the lab to try to do this kind of thing, I use my oscilloscope and I'll measure, I use what's called the cursors on the oscilloscope to make a measurement. You guys probably don't know how to do that. You know how to push the auto set button, right? And that's not a good thing. The TAs don't know how to use the oscilloscope. That's the problem. Back in the days when we were real, we would measure with the cursors, and we'd see that the time between those two peaks. Looking at this picture, what's it look like those are? Well, it's 0.1. I mean, yeah, it's 0.1 if you looked at it carefully. So what I see here is that from that, this is my t. My t equals 0.1 seconds. So what's my f? What's the frequency of that? 10 hertz. And then, I don't know. I usually don't care enough to then figure out that's 2 pi times 10t. So 20 pi, I don't know, there's some number that I don't care. It's 2 pi 10. All right, and plus phi. How do I figure out the phi? I told you to figure out phi. How would I do that? Yeah, well, figure out how far it's shifted over. How could I figure that out? Looking at that picture. If I gave you that picture, how would you do it?
I'm concerned about t. This you determine t equal to 0.1 of the time.
Yeah, I looked at the x-axis. Basically, how long did it take to get from that peak to that peak? Which if I looked at that carefully, so it looks like it's at about, I don't know, 0.09, and then it's happening here at about 0.19, right? It's about, I mean, it is that. I'm making up those numbers a little bit, but if I look at it carefully, that's what it is. So how do I figure out what phi is?
You look where cosine should be and like where it is, like so a basis, like a regular cosine wave compared to this.
Well, so let's try a t equal to 0. But I mean, you got the right idea. Let's say I plugged in t equal to 0. So I said x of 0. Looking at this picture, where is x of 0? It's about 7. Turns out it's not quite, but let's call it 7. All right, and that's got to be equal to 10 cosine what? Omega t. So omega is 2 pi 10. Well, what's t at t equal to 0? 0. So this is basically cosine phi. And what do I have? I have cosine phi equals 7/10 or 0.7. It's actually, if I look at it carefully, it's 0.707 where it's actually at. So this phi value, let's see if anybody knows what that phi actually is. So at 0.707, what angle has a cosine of 0.707? Anybody know? That's the square root of 2/2.
That's 45.
That's 45 degrees. Yeah, phi is 45 degrees. All right. Okay. So that's a phase shift there of 45 degrees. So this is the actual waveform. Now, one term that we use a lot is, I say that that is shifted ahead in time. All right. It's like a cosine that's been shifted forward. Now, that's a little bit weird sometimes for people because they think, well, shouldn't shifting it, so in other words, it's a cosine omega t that has been shifted to the left, right? I shifted cosine to get to the left to get this thing, right? That's a shift forward in time. The reason I say forward in time is because the peak of cosine is happening at an earlier time, right? That's where I'm getting that, the usage of that term. So one thing that we're going to use, I hate the term, but it's used a lot, particularly for power stuff, is we talk about leads and lags, all right? And they talk about this whole notion of current leading voltage or lagging voltage or what have you. All right, so this is an example. So our reference wave is the blue here. The reference, what is that reference wave? There, what is that? If I told me, give me a function for that thing. It's cosine, right? This guy looks like V2 of t, looks like he would be V sub m cosine omega t. And I don't know what omega is in this case. It's been defined generically, right? So the green and the red are shifted from cosine, right? Now, if I shift to the right, sorry, shift to the left, okay? If I shift to the left, I call this a lead, right? I'm saying that waveform leads because he peaks earlier in the cycle than the cosine does. And I say that this red one lags the blue one, all right? Because he peaks at a later time. And we use those terms a lot when we talk about voltages and currents in our circuits, all right? So I got a lead and a lag. So in this context, right, if I'm looking at the red one here, all right, it's told me that this guy would be Vm cosine omega t. Now, am I shifting him to the right? He's lagging. So how do I represent the shift here as an addition of an angle or a subtraction of an angle? Subtraction of an angle, right? And it turns out that in this particular case, it's 45 degrees. Now I should be super careful because I got two different units here, right? What's the units of omega t? Radians. That's got 45 degrees. All right, math guys would be freaking out at me about that, right? No one says degrees per second, so I never do it that way, but no engineer ever talks about pi over 4 radians either. All right, when you go to Duke and you say, well, the voltage at that bus is negative pi over 4, you'll be out of a job. All right, they'll say 45 degrees. That's probably not true. They wouldn't have hired you in the first place. All right. So, all right. So we'll use that concept of lead and lag, as we go through for stuff. But it's important to remember. All right. So let's look at an example here. So I want to figure out what this guy is. So I want to get everything in the context of this. So this is x of t equal to x sub m cosine omega t plus phi. All right. So I want to figure out what x sub m, omega, and phi are. And I hope I wrote this for myself. I think I did. All right. So how do I calculate this guy here?
Find the period.
Yeah, period. Well, so period and amplitude are easy to find, right? So yeah, and even simpler than that. I want to do the amplitude first. X sub m, what's that? 10. All right, you should always be able to get that one, hopefully. All right, that guy's 10. And I guess this is V of t. As I've written, it's all right. V of t. All right. All right. So yeah, the next easiest one probably is to get the omega, which I start because I'm looking at time. I start with the t. So how would I do that? How would I do that? How would I get the period? Well, it's marked out some nice values for me on it, right? How can I use those values that's been marked out? Subtract what? Yeah, so the function repeats. How quickly does it repeat? So I have the negative going zero across and negatives going zero across. Right there, marked out as 6.2 milliseconds and 26.2 milliseconds. What's the time between 26.2 and 6.2? 20 milliseconds. Okay. So what's the period? Or yeah, what's the frequency? 1/20 milliseconds, which is what? Anybody know what 1/20 milliseconds is? 1/20, well, 1/20 milliseconds works out to be what? So it'd be 1/0.02, which is 50 hertz. Okay. So 50 inverse seconds, I guess, right? That's the other way you could think about it. All right, so 50 hertz. And I know that because that's nice European power frequency, all right? In the US, what's the power frequency? 60 hertz, okay? All right, that's what it would be in Europe or most of the rest of the world, 50 hertz, okay? So, all right, I've got that. How would I get omega then? How do I go from F to omega? 2 pi F, right? So that works out to be, I don't know, I'm going to call that 100 pi. Again, I don't really care what it is. All right. In general, I don't like keeping stuff symbolic like that, but I don't really care about what radians are. All right, so what else? I got to figure out phi. Phi is the tricky one here. How do I figure out the phi? Well, in this case, what I would do is phi tells me again how much I'm shifted from just cosine. So in this case, is the phi, is it positive or negative here? It's negative because I pulled it backward in time, right? Backward in time, meaning that peak is happening at a later time. All right, so it's a negative. Phi is going to be negative. And the way I can calculate that is I can always calculate my angles using this omega t. So what I'm going to say, this omega times time is going to tell me an angle, right? So in this case, the shift that I've got is 1.2 milliseconds, right? It was shifted to the peak is happening 1.2 milliseconds after zero. So I can say basically what? I can say that this shift would be omega, which is 100 pi, times the shift that I have, which is 1.2 milliseconds, which is, if I do the math on that, that works out to be what? If I wrote down the right answer, I think it's negative 21 point. So it's 21.6 degrees. Somebody just do the math. What is that? 100. I'm not sure I wrote down the right number here. So 100 times pi times 1.2 times 10 to the negative third is 0.377, like that. All right. And that's in radians. All right. Now, I said this is negative too, right? The phi is actually a negative value here because it's being pulled to the right. Okay. So, you guys follow what I just did there in terms of that calculation? So I wanted to figure out how much of an angle shift that 1.2 milliseconds was. So I basically said, okay, well, the angle shift would be whatever the frequency is in radians per second, how fast my angle is advancing with respect to time, times the amount of time shift. All right, so I figured out that that's 0.377 radians. You guys with me? So again, if I, yeah. This would be what I call, this would be, it's lagging a cosine function at least, right? I would call this lagging with respect to that cosine. Usually when we say lagging, we got to say with respect to something. So when we get into the power stuff, we'll say, is the current lagging or leading the voltage, right? So in this case, yeah, this is probably a lagging setup here. Well, it's always, I don't want to focus too much on that term just yet. It's a question of, is it being shifted to a later time? If it's shifted to a later time, it's always going to be negative. Yeah. We'll talk a lot more about that leading and lagging concept later. I was just kind of introducing it now. You're not going to have any questions right now about leads and lags. All right. Not till towards the end of the semester. When I have this result right here, I don't like this in radians. So what do? How do I convert that to degrees? What would be the conversion to multiply that by? Multiply by what? 180 over pi. Yeah, I would multiply this guy by 180 over pi. So I would take negative 0.377 radians times 180 over pi, and that would become, I think that's negative 21.6, I think. All right, is what that works out to be. Okay. All right, and that's typically how we would write this sort of thing. That's the kind of question you might get even on the next exam. All right, something pretty basic on this concept. All right, I would expect you to see something like this on homework 4. Okay. All right, now we go through all that because, yeah, we got to understand all this stuff, but we did this the other day. I said, okay, if I got a static circuit like this one here, so I simulated this guy, static circuit, it's a voltage divider. First of all, intuitively, without doing any analysis, all right, the input is V in 10 sine 2 pi 100t. You should be able to do this without thinking. Is V out, which is the voltage across R2, is it bigger or smaller than V in? Smaller. If you can't answer that, think hard about it, right? What is this? It's a voltage divider, right? So it's a divider, meaning it's going to make the voltages smaller, right? It's going to divide them down, right? So again, you may not remember the formula for that off the top of your head. The way I remember it, again, as we move into probably next week and the week after and the week after and the week after, probably the next like 3 weeks or so, we're going to be doing a lot of 2111 with resistors, inductors, capacitors. We're going to be doing voltage dividers, current dividers, mesh, loop, all that stuff. We're going to be doing it again, except we're going to have complex numbers in this thing. All right, so there's going to be a lot of review of that stuff. By the time you get to the end of that, you should intuitively start thinking, okay, if I got a voltage divider, this voltage is going to be smaller. It's never going to be bigger. All right, it's going to become a smaller value. All right, and how would I figure out that it's a smaller value? What would be the formula here? What would the formula be? And yeah, you guys can try to remember what the formula would be, but you should intuitively, if you didn't remember the formula, good for you. You shouldn't remember the formula, right? How could I figure it out? If I asked you to tell me the voltage across this thing, do it for me in 2 steps. What's the first step? Yeah. So he's right. So it's do it for me in 2 steps, right? What would be the first step? So if I got V in and I got R1 and R2, what's
Total current.
total current, right? So that's how you get the over R1 plus R2. And then I multiply by R2 because I do I times R to get the voltage. Right. So that's my voltage divider relationship. So V out better be R2 over R1 plus R2 times V in of T. No memorization for circuits. All right. There's nothing to memorize, right? I should be able to think through all those steps, right? Rather than trying to memorize some kind of formula. Okay. All right. So that's what it is. So what's that V out going to look like? If V in was 10 sine 2 pi 100t, what's the output V out going to look like? If I looked at it on an oscilloscope, what's its frequency going to be? The same. Its frequency is not going to change, right? What's its amplitude going to be? It's going to be smaller than 10 because it's being divided down. What would the current look like? What would its frequency be? Be the same, have the same frequency, and it wouldn't be shifted at all. There's nothing in this circuit, in this quote unquote static circuit. I said, what makes it static?
So energy storage element.
No energy storage elements. There's no dynamics to this thing, right? It's just basically burning heat, right? It's basically just a bunch of light bulbs, doing nothing particularly exciting. Okay. So in this particular case, what I should see is that all of the voltage and currents have the same frequency. They have different amplitudes, and they have the same phase. All right. They're not shifted relative to each other at all. All right. That's always going to be the case if I have these sort of static circuits. It tells me that if I want to analyze these circuits, do I even need to keep that sine 2 pi 100t? Did I need that for any of this analysis? No, I didn't. I could have just done all the analysis on the amplitudes. Okay. So that's nice. It tells me that I don't actually need to worry about the time domain stuff in this case, which is nice. All right. Now I will have to worry a little bit once I get into L's and C's, because there will be shifts. All right. So that part I need to take into account. But if I had resistors, it would be nice. I wouldn't even need to worry about the time piece. I could just track what the amplitude's doing and make my math simpler. Okay. All right. So the other day we looked at this guy. All right. And I said, well, I've got an RC in series, and I gave this thing a name. I called this guy a low pass filter. All right. For reasons that we're going to talk about in the second half of the semester. All right, what this guy does is basically I put cosine 2 pi ft. That could be an audio signal or something like that. And I'm measuring what that audio signal looks like at the output of that capacitor. So across that capacitor, right? And so I got a 15.9 kilo ohm resistor and a 1 microfarad capacitor. And what I said was I was going to change F. And I think I used F as 0.1, 10, and 100. Right, I can't remember. I got them here, but I used 3 different frequencies, and I saw that there were some changes that happened. Okay, now because this guy is a dynamic system, in other words, R's and C's, he's got energy storage. What's going to happen with energy storage? Well, I need to write a differential equation. If I write a differential equation, that tells me, why did I write a differential equation? Well, because there's energy storage. What does that mean? Well, in DC circuits, right, there was a steady state response, right? The steady state response, when does that occur? When does that apply? After the capacitor is fully charged. Same thing sort of happens here. The capacitor doesn't get fully charged in the sense that the voltage becomes constant, but it gets fully charged in the sense that in steady state, the solution to it becomes basically some value like this. So I skipped ahead there for a second. I said, if I wrote the differential equation, or you can look at the math later if you want to, right? I did a KVL to get to that. I get to this differential equation. Okay. And what I see is that in steady state, the capacitor doesn't get charged in the sense that the voltage becomes constant, but it gets charged in the sense that the transient is what? What's true about the transient response? There's always 2 parts of the response, right? The steady state is where I get to eventually. After the transient is what? What's the transient always do? Go to 0. The transient always goes away, right? The whole thing, intuitively, solving differential equations is no fun. Nobody likes to do it, all that kind of stuff. You're never going to remember how to do it in a couple of years, right? You won't even remember it in 6 months, probably, right? But the key thing is, what does it tell me? Why does it even exist? Because basically, that thing I always say about the capacitor voltage stays continuous, the inductor current stays continuous. Basically, the inductor and the capacitor fight off changes in the voltage and the current. They fight them off, right? Because of just the principles of thermodynamics, right? And how they work. And so this transient response represents sort of how the capacitor fights off that change from one condition to another steady condition. All right. And so it always goes away. And if I have a first order system like this, what's it look like? What is the general form of the transient response that I would get? Yeah, it's gonna do that, right? What is it? What's the general mathematical form for it? It's exponential. And I don't know what its amplitude is. That's some constant I got to figure out. And so that's E, how do I write E, what's this, E to the negative T, better be negative T over tau, where tau is the time constant of this thing. And it always better be negative. If it's not negative, what's true about that transient response? It's exploding, all right? And it's, in other words, it's not transient, it's not going away, right? The circuit's gonna be on fire, all right, or something, okay? And that, you know, those things can happen in reality with some help, all right? They're not gonna happen to you in the lab, but they can happen under certain conditions. We can talk about that separately. There are conditions that can cause that to happen, but and you need to be having some kind of an energy source that's there, like a battery or something connected to your circuit to make that happen. All right, but it can happen. And we went through this the other day. I said, well, 0.1 hertz, I can see the transient response there, and it's gone after a little while. In this particular case, at 0.1 hertz, what I see is that input voltage and output voltage basically look the same. That kind of makes some sense a little bit if you think about the capacitor. In DC circuits, we said if the capacitor was in steady state, we said it was an open, right? So at a really low frequency, we're going to talk about this later, but a really low frequency, the capacitor sort of looks like an open, and basically the input and output look the same. As I get to a higher frequency, 10 hertz, I can still see the transient there. The transient's gone now, right? And I get to this sort of state right here. So when I say the transient's gone now, I said the transient was going for a couple of periods, maybe, or one period, right? How long does it take for a transient to be gone? Well, in theory, forever, right? It goes to T, to the limit as T goes to infinity, but after about 5 to 6 tau, thereabouts, it's over with. Right, it's negligible at that point. So there I have it. What's happened to the output voltage there? Two things have happened, right? Has the frequency changed? Those guys look like they have the same frequency. Their timing is the same, right? What's happened? It's been shifted, right? And its amplitude has been made smaller. So it's been scaled down and it's been shifted right. Okay. And if I look at 1,000 hertz, what do I see? Well, it's definitely smaller. And in fact, it's been shifted more. And in this case, if I look really carefully, it turns out it's been shifted about 90 degrees. All right. In other words, where this guy is peaking is about 90 degrees after where the blue is peaking. All right. That's what I can see. You know, you wouldn't probably see that, but I see that it's a quarter period shift. The way I can see a quarter period shift is one peak is happening where another zero cross is happening. All right. Again, that's just something I know from a lot of experience. I wouldn't expect you to see that, but what I see is that there's shifting that's happening, right? So here they're lined up. Here there's a little bit of a shift. Here there's a lot of shift. Okay. So basically, this is kind of the summary, right, that we have, right, for this stuff. And we're gonna see this as we shift into the next part of the class. What we're gonna deal with is I'm gonna start thinking about, all right, the time domain part of that whole thing. So I have this whole function cosine omega t plus phi, and then some amplitude. This omega t piece has nothing to do with what happened here, right? All right. In other words, to analyze this thing, I only needed to capture two things. I needed to capture what happened to the amplitude, and I needed to capture what happened to the shift. All right. So it turns out that I don't need this information most of the time. Now I need it if I'm going to solve the differential equation to get the transient response. But the fun thing is that we're going to not worry about the transient response really ever, unless we have to, which for this class is never, right? After exam 2 and the final exam. All right. But for most analysis that we do, we only worry about the steady state conditions. And if I worry only about the steady state conditions, I just have to track what's going to happen to this phi and what's going to happen to this amplitude. And we can make some simplifications, some pretty nice simplifications if we do that. All right. And we're going to start talking about that later. But this is sort of the key result, which is basically with sinusoidal voltages and current sources. Our steady state response is always a sine or cosine wave with the same frequency that will be scaled vertically and shifted left or right. And that allows us to jump into something that we are going to call phasors. All right. All right, now I want to talk about one thing real quick. I'm going to wrap up with this on Friday and start talking about the phasor concept. All right. But before I do that, I want to talk about this thing about shifting from sine to cosine. There's a trig function that will relate cosine to sine. But I keep, it's normal to do this. We relate everything to cosine. In other words, if I give you a sine function, you will ultimately always need to shift it to a cosine function. And we'll talk about why over the course of the next week. All right, but there is the very last part of the last problem asks you to tell me the phase shift for the equivalent cosine. I want to talk about this real quick. If I gave you sine of omega t, and I told you to give me the equivalent cosine, there is a trig identity. You can go and look it up. But the way I think about this is, what would I have to do to cosine to turn it into, or sorry, what would I have to do to sine to turn it into a cosine function? Or sorry, what would I have to do to sine to turn it into cosine? Shift it. And actually the derivative statement is actually is telling me the same thing as the shift. All right. If I shifted sine backwards in time, all right, to turn it into cosine, right? Or if I shifted cosine forward, all right, I could be careful. I guess my shift to the left is actually forward. My shift to the right is actually backward in time. To turn cosine into sine, I would have to shift it by 90 degrees. And I'm getting the 90 degrees. You can intuitively see it because where sine is peaking, cosine is zero crossing. That's a 90-degree difference. All right. So what I see is that if I took the cosine function and I pulled it forward, so I pulled it backward 90 degrees, shifted it to the right 90 degrees, that would become sine. So because I need to pull it backward in time or move it to the right, it's a negative 90 degrees. All right. So sine omega t is equal to cosine omega t minus 90. If I gave you sine of omega t plus 10 degrees and said, give me the equivalent cosine, what would that be? It'd be cosine of omega t plus 10 minus 90. Because I got to take it and shift it 90 degrees to the right. So yes, it becomes cosine of omega t minus 80 degrees. And again, there's a trig identity for that, but intuitively, I look at that picture. I just draw out sine and cosine. And I say, how much do I have to shift cosine to get it to become sine? All right, I have to shift it to the right 90 degrees. And I can apply that then to, if I give you something like I did in the homework, where it's probably, I don't know, cosine of omega t plus 48 degrees or something like that. All right, that would apply. Okay. All right, so that's it for today. Again, office hours will be tomorrow night, Discord. If you guys reach out, use the Discord channels to talk to each other or whatever, or to talk to me, that's all fine.